Good afternoon, everyone. I'm Ann Aylward, Director of the U.S. DOT Volpe National Transportation Systems Center. Welcome to Up and Away, Innovations in Advanced Air Mobility. This is the third event in the U.S. DOT Volpe Center FAA series, and today's session is focused on urban air mobility concept of operations and one of the strategic goals of the U.S. DOT's transformation. Today, I'm pleased to welcome Paul Fontaine, Assistant Administrator for Next Gen Air Transportation at the FAA, Robert Pierce, NASA's Associate Administrator for the Aeronautics Research Mission Directorate, and Steve Bradford, FAA's Chief Scientific and Technical Advisor for Architecture and Next Gen Air Transportation System Development. Achieving changes in the transportation system necessary to reach our goals will require fundamental transformation to our infrastructure, our technology, and our approaches to solving problems, as well as a renewed commitment to science, learning, and innovation. After Steve and Bob finish their talks today, we'll have a question and answer period. Please type your questions for speakers into the Q&A box as we go along. We'll get to as many of them as possible. It's my pleasure now to introduce Paul Fontaine. As Assistant Administrator for NextGen at FAA, Paul is responsible for championing the evolution of the national airspace system. He provides strategic direction and executive oversight to more than 800 federal employees in the Office of NextGen and is responsible for implementing the air transportation system modernization, executing the aviation research portfolio, and delivering results to support the overall advancement of aviation. He has experience harmonizing the implementation of aviation technologies with stakeholder priorities and ensuring that risks are collaboratively addressed to facilitate delivery of next-gen capabilities and benefits. Paul, the floor is yours.
Okay, well, thank you very much, Ann. As Ann said, the NextGen organization is really responsible for moving innovative ideas and technologies through a developmental phase to implementation, and helping enable basically the safest, most efficient aerospace system in the world. But as we know, we're also catering to an ever-growing set of users that are operating inside the national airspace. So as such, the NextGen is really the agency's focal point on advanced air mobility, helping to organize and coordinate really a wide array of activities across the FAA that will be needed to support the development and implementation of an ecosystem, which will be needed to support advanced air mobility. And as such, we have lots of partners, right? So the FAA, NASA, and Volpe have a really proven track record of working together to advance aviation. We also collaborate very closely with other federal agencies, with academia, with industry, to really try and maximize the impact of our really comparatively small research and development resources. But these interactions provide us with a great background and data needed to help inform FAA's policies, standards, certification, integration requirements, and other things in support of really routine AAM operations in the future. For us, it really begins with the conceptualization of a future end state, taking that idea and conceiving it, validating it, and articulating it. And the FAA has shared a lot of that information about our vision for AAM, operational concepts, and implementation requirements that will be needed to enable these capabilities. The UAM concept of operations provides a technical roadmap from a near term to a mature state for what we see will be needed for enabling UAM operations. We published the initial version of UAM concept of operations in 2020. And earlier this year, we released ConOps 2.0, which is an evolution from the initial concept or initial version that was developed through feedback from the FAA, from NASA, and from industry partners. It also emphasizes the government industry collaboration that will be needed for continuous improvement. And we expect that as we continue to mature, get these things into the field, we'll continue to update and validate basically that concept as things mature. So along with our industry partners and stakeholders, we recently validated some of the elements of the UAS ConOps through live flight demonstrations in California. This demo successfully showcased industry-developed concepts and proposed solutions for managing UAM operations alongside traditional ops. We continue to use demonstration activities to give shape and definition to these new ideas, and more importantly, to build consensus amongst the user community. So while we envision a near-term AAM operations will include a pilot on board the aircraft, our ConOps also call for more automated and more autonomous operations as AAM evolved into a mature state. So toward that end, the FAA is now leading an autonomy working group to prepare for autonomous operations in aircraft into the future. This work will lead to determining our collective set of requirements and capabilities that will be needed to address these needs. The autonomy topic is going to be a future episode of the FAA's AAM webinar series, and you can find more details about that on our websites. So as you hear more about the UAS concept of operations today from both Bob Pierce and from Steve Bradford, keep in mind that we will continue to work in close partnerships with other agencies and with industry to help validate the UAS concepts and those requirements, and making sure that we're on track to enabling safe integration of AAM into the national airspace. So with that, thank you all. Happy holidays, and I'll turn it back over to you, Ann.
Thank you very much, Paul. Our first presenter will be Bob Pierce, Associate Administrator for Aeronautics Research Mission Directorate at NASA. Bob manages NASA's aeronautics research portfolio and guides its strategic direction, including research in advanced air vehicle concepts, airspace operations and safety, integrated aviation systems, and the nurturing and development of transformative concepts for aviation. Bob has experience in all aspects of aviation research and development, including serving as Deputy Director of the FAA-led Next Gen Joint Planning and Development Office. He began his career as a design engineer at the Grumman Corporation, working on such projects as the Navy's F-14 Tomcat fighter and DARPA's X-29 forward swept wing demonstrator. Bob, thanks for being with us, and the floor is yours.
Thank you, Ann. It's great to be here. And
always great to have you.
And I thought I'd, in addition to advanced air mobility, which is absolutely an important and exciting topic, I got a couple of charts in the front just to kind of give you a sense of where we are in aeronautics within NASA generally, and then I'll pivot over to advanced air mobility before I turn it over to Steve. So I go to the next chart. So some of you may know we have a long-standing strategic plan that cuts across all aspects of aviation, everything from our support to FAA for the future of air traffic management, to high-speed flight, to ultra-efficient subsonic aircraft, subsonic transports, airliners, and so forth. And then, of course, over to what we're doing in advanced air mobility, safety, and autonomy. So across the board, we work closely with industry. We work very closely with the FAA and academia to make all these aspects of what we envision reality. Next chart, please. It sort of can be summed up in these four sort of visions. One is we're looking to enable the next generation of ultra-efficient airliners, and I'll say a little bit more about that to show you an image. But basically, it's sort of there in the foreground that transonic truss brace wing is a next generation concept that we believe could help usher in a new era of extremely high efficiency transport that will marry up with the development of sustainable aviation fuels to bring aviation to net zero emissions. In the lower left, you see high-speed commercial flight. So obviously today there is no commercially available high-speed reach supersonic flight. That's because there's a lot of hurdles, environmental and economic and other hurdles to enabling that to occur. NASA's, carefully and slowly trying to overcome those hurdles. And the first one we're trying to overcome is overland noise or the sonic boom. See if we can't soften that to a point where it'd be acceptable. And I'll show you an image on that. And then the upper right, future airspace and safety, where we probably have our largest partnership with the FAA, very long-standing, as we do work at fundamental level to look at automation that can help improve the efficiency and the safety of the system. And then we work closely with the FAA to transfer that to FAA for application, or to airlines or others, depending on the nature of the automation we're researching. And then, of course, at the lower right is advanced air mobility, which is why we're here, and we'll talk more about that. Next chart. And I wanted to emphasize that in addition to those, we continue to nurture an innovation ecosystem that is always looking to what's next, to what is beyond those visions I just talked about, so that the future of aviation remains bright. So I won't go through these particular images here, but we're working at low TRL. We're engaging with universities. We're engaging with other agencies, with the research community in general. So it's not just our researchers, but it's the entire community coming together to invent the future. Next chart. So I'm going to show you a couple images. This one is what the work we're doing on the future of efficiency. And again, I won't belabor it, but just to say that image there, that transonic truss brace wing, in and of itself could deliver 10% more efficiency. And across the board, what we're doing with weight reduction through composites, increasing energy efficiency, could lead to a 30% more efficient airframe for the future. That particular image, that transonic truss brace wing, we have awarded an X-plane contract to the Boeing Corporation to actually go out and, in partnership with NASA, build and fly that, and actually prove that we can get the kind of efficiencies that I was just talking about there. So that's a really exciting activity got ongoing. We plan to fly that in 2028, and it's been designated the X-66. Next chart, please. And here's the X-59. This is the one that's going to go out and demonstrate that we can reduce sonic boom to an acceptable level. So here we are just about at the finish line in terms of having that airplane developed and get it into flight. And it will actually, it's been designed to deliver a very low sonic boom, something that you might consider like a sonic rumble or a sonic thump, something that we think can be acceptable to communities. And we're going to go and fly that and actually do scientific surveys to see if the noise is acceptable. So we're getting close to flight. We plan to fly first flight in 24, and then we'll have some work to do to expand the envelope and so forth before we go out and fly over communities. Next chart, please. So with that, let me switch to advanced air mobility. And of course, this is enormously exciting. It's got a lot of use cases, everything from urban air mobility, which is, could be air taxi type operations, could be first responder type operations, could be interregional operations. Even in the background, I'll show you a chart later about we're taking some of these concepts and some of this technology and seeing if we can't better support wildfire operations and create more efficient, safer, and more effective aircraft operations in the wildfire as we're fighting wildfires. Let's see. So next chart, please. So along those lines, I just wanted to, and Steve is going to go into details on the CONOP, so I'm not going to do that here, but the kind of things we've been doing over the last couple of years listed here. As Paul said, FAA just released CONOPS 2.0. And of course, a lot of our research findings that we have been working over the last several years, we have documented, published, and certainly provided the FAA to increase the fidelity and the completeness of the CONOPS. And one example is demand capacity balancing in urban areas. We've also released an airspace research roadmap, a UAM airspace research roadmap that is aligned with both industry and FAA CONOPS that identifies high-level requirements and research needs. And so now we have that available, not just to NASA, but to the entire community to be able to create a consistent and a collaborative approach to solving the challenges associated with UAM and AAM. We've been working with standards organizations, including ASTM and so forth. In this case, what's listed is the industry standards for provider services for UAM, for the folks that would actually operate systems. And you can see up at the right-hand corner there is a very high level notional view of what a UAM architecture would be. And of course, the standards around that are what's really of interest. And then we have actually developed, just one example of a technology that we developed is a UAM arrival departure scheduler, a set of requirements within a UAM federated architecture that would fit within that architecture that was shown above. So a lot of accomplishments just over the last couple of years. We've built out an entire roadmap between now and the end of 2030 that will have a series of demonstrations that bring technologies, bring architecture together and actually demonstrate it in an incremental way, similar to how we did UAS traffic management not too many years ago. All of that will help validate requirements, validate concepts, validate technologies, and that will all bring the industry readiness up for operation, and certainly FAA's ability to take this and to turn it into operational procedures and standards and so forth. Next chart. In addition, we haven't walked away from U.S. traffic management, and of course, FAA is working on beyond visual line of sight rules. So we have recently partnered with them on their key site activity down in the Dallas area, where we're providing a network that the UTM service suppliers can link into and actually demonstrate operations and demonstrate beyond visual line of sight operations, and then gather that data, analyze that data, and make sure that's all available to the FAA to support rulemaking. So we're really excited about this recent development, and really hope that that the partnership between FAA, NASA, and industry will lead to what is really sorely required, which are those beyond visual line of sight rules. Next chart, please. And I just want to mention too that, in addition to airspace and safety, which we work heavily again with the FAA, we also work technology. We've been developing an X-57 now for a number of years. Unfortunately, we actually decided that we're going to end that project before we get to flight, but it's delivered a tremendous amount of benefits relative to publicly available information that have informed standards operations, best practices for design, for testing, and particular technologies. So, for example, there have been several commercializations, one on aviation quality batteries that has come out of this, that have led to tremendous benefits of pursuing this X-57. But we decided that industry has made sufficient progress that going to flight really wasn't going to substantially add additional benefits beyond what we had already realized through the ground development, ground test, and our interactions with the standards development community. But we'll continue to do additional work, ground-based work on reliability of powertrains, on crashworthiness of these kinds of systems, especially with very high energy batteries on board and so forth, and a number of other areas to continue to push the state of the art in the aircraft technology itself forward for application to next generation airplanes. Next chart. And then I wanted to mention that, as I said earlier, all of this development has provided us a suite of technologies and architectures that when we kind of stood back and looked at it, realized that if we were to bring this to the wildfire manager, could really provide a revolutionary capability to better fight wildfires, which is obviously a national crisis. We did this at small scale with a little project we call Stereo, where we built UAS pilot kits based on the UTM technology we had already developed. made portable pilot kits, brought those out to the field. We're actually able to work directly with the wildfire manager as wildfires were occurring to operate small UAS. And now we're in the process of documenting those requirements, or we have documented those requirements, and those have been transferred to the wildfire community so that they can go out and build these small pilot kits, and they can actually go out and operate UAS during the wildfires. But there's a much bigger vision to be had, as you can see by this chart. The biggest thing is today, all aviation operations for wildfire management occur during the day. But in talking to the community, they would really love to be able to have nighttime operations and low visibility operations, especially at night. They talk about how the fire is more manageable, and they were able to get over those fires and drop water and so forth, do search and rescue at night. They would be able to be much more effective. In addition, you can think about pre-positioning equipment where it's needed to be positioned using these kinds of assets. And of course, using aviation to do remote sensing, real-time sensing, so that wildfire prediction, the movement of the wildfire can be much more accurate. So there's a lot of things that better aviation operations during wildfires can bring. And it's all a result of the work we've been doing with UAS and UTM and now advanced air mobility, showing that these technologies not only can be tremendous commercial assets and tremendous economic benefit, but can also deliver really critical public good. And I think the more we focus on these areas of public good, the more we can deliver those in the near term, the more support we'll see overall for having these kinds of operations more generally. And next chart. And I think that's it. Just a really quick overview of the kinds of work we do. A lot of excitement across the board and the things we do in aviation. I mean, here's all the ways in which you can follow us, and certainly appreciate the opportunity to talk to you today, and look forward to taking your questions. And with that, back to you, Ann.
Thank you, Bob, for a really interesting presentation. Our next presenter will be Steve Bradford, FAA's Chief Scientist for Architecture and Next Gen Development. Steve is chairman of the Technical Review Board, which monitors technical decisions, related investments, and the enterprise architecture. He works with elements of FAA to develop midterm plans and 5-year budget requests to implement Next Gen. He is FAA's lead for the FAA NASA Research Transition Team process that supports collaboration between the FAA and NASA on ATM-related activities. Steve also has a leading role in international engagement activities related to Next Gen at the International Civil Aviation Organization, ICAO, and CSAR joint undertaking, a European partnership. Steve, over to you.
Thank you, and I'm going to go a little bit more detail on the UAM concept. Next slide, please. So, as Paul said, the UAM concept was published in earlier this year, Concept 2.0. And just to point out, we focused on crewed and uncrewed aircraft operations, carrying passengers and cargo at lower altitudes in and around major metropolitan areas. The difference between UAM and AAM, AAM is the larger class of aircraft that we see coming and with new operations. UAM is really trying to address locations where we will have dense operations in which potentially the ATC system is not scalable. It'll address incorporation of these into the NAS where traditional operations exist. This is not like UTM, which is 400 feet below, which is outside the world of ATC, but these will be in the midst of ATC. And we'll consider the evolution of aircraft technology and increasing levels of automation. Next slide. So just to put it in context, we like to talk about diverse operations that are coming. At the bottom, you see the UAM, UTM, unmanned traffic services. That's the 400 feet and below. That's where we have the VLOS and BVLOS that Bob talked about. At the top, we have the transit to space. We have the higher airspace operations. We're beginning to see more and more and more high altitude, long endurance aircraft that fly nominally 60,000 feet and above for up to 110, 120 days. Very slow movers with the evolving potential for supersonics to be in near that range, and they'll have to interact. We have our traditional air traffic separation services, and then down below at the lower altitudes, 1,000 to 5,000 feet, we'll have the urban air traffic services, which will be an important new entrant in the NAS. Next slide. So we envision that we will end up with two different worlds, or three different worlds, or four different worlds. We'll have the traditional ATM air traffic management system, where air traffic provides the separation services, the traffic flow, the advisories, and develop the infrastructure for the ComNav and surveillance. We also see on the right-hand side the need for extensible traffic management services. What I mentioned at the ETM, that'd be the people flying 60,000 feet and above, the UTM, the 400 feet below, and then the AAM, UAM, where we see the infrastructure and the operations being managed through third parties. It'll be complementary to ATC. It'll provide the scalability, the flexibility, and the near-term agility we need in order to support these operations. Next slide. So our concept is specifies a type of cooperative operation that occurs within what we call cooperative areas. An example would be the definition of a UAM corridor or a pathway. And it's conducted in compliance with specific rules, procedures, and performance requirements, and operated under what we call cooperative operating practices. And we'll get back to that, that's key. And any aircraft utilizing this area must participate in this federated ecosystem by attaining a confirmed operational intent from the provider of service for UAM. You must share your intent. You must deconflict your intent strategically from other operators. Part of the reason for that is what Bob mentioned before. They're building the departure scheduler. That would be for the industry, because these aircraft have a much different operational envelope. They really have to be able to know that when they depart, when they're going to land. They don't have the holdover times. They don't have the ability to vector. An aircraft operating within these corridors must meet the performance participation requirements of the UAM environment. And most importantly, these areas will exist in all classes of airspace. We're not talking about a new class of airspace. We're talking about you participate in the existing class of airspace, but with the cooperative area, you'll have additional requirements. This is not to say that every eVTOL has to participate in the cooperative areas. This is a matter of choice, and in some locations it will be unnecessary. You'll be able to operate still within ATC, except when we get into the world of autonomy, which Paul mentioned earlier. Next slide. So this is really about the operator maintaining the separation. So they'll coordinate, execute, and manage their operations. One of the principles is they have to use the airspace efficiently as practical. Your intent has to be not only known, but it has to be well enough defined so that you're not occupying too much airspace with a large buffer. You have to share your intent information with all relevant stakeholders so that they can also plan their operations. You will comply with this set of stakeholder developed cooperative operating practices. Once again, I'll get back to that. You'll have to comply with the applicable performance and regulatory requirements for the airspace in which you're operating. When you're operating Class B, since you're operating in the ATC airspace, you'll have to be equipped for Class B. That's what that means. And you must maintain conformance to the intent communicated with other stakeholders. It's like PBN in that you have performance, but it's not only lateral, longitudinal, altitude, but also a long path, your intent. Next slide. Now, we don't expect the operators to be able to do this by themselves, so we believe that there'll be some providers of service for these operators. They will work together as a federated system to manage the operational intent submitted by the operators. And they will help with the rules. They'll help deconflict them strategically. They'll provide the operators with information relative to their planned UAM operations. That could be local weather, other airspace conditions. They have to share this confirmed operational intent through the federated service network. This is like the network that we're trying to build in the demo in Dallas, which is this will be owned by the industry, and they'll use this federated service network to share their intent and the information. They have to comply, once again, with the performance and regulatory requirements, and they have to support cooperative separation management services. The cooperative operating practices will specify how you separate yourself, both tactically and strategically. Next slide. Now, that's not to say that because we're setting up these cooperative areas that the FAA is no longer involved. We maintain regulatory authority over the airspace and operations. As one of my predecessors like to say, this is our airspace and we love it. We provide guidelines and approves or acknowledge the COPS in accordance with our statutory responsibilities for equity, safety, and security. Whatever the community comes up with as community operating practices will be reviewed to make sure they maintain safety and security, but most importantly, well, not most importantly, but additionally importantly, equity. The rules cannot favor one operator over another. We will then have to qualify third-party suppliers of services for use by the UAM operators to meet the regulatory requirements. And that's key, and that's part of the demonstration we're doing in Dallas is to qualify UTAM service suppliers. This will rise up into the UAM cooperative airspace. And we have to establish performance requirements for the cooperative airspace. And we have to confirm that the operator meets those standardized levels of performance. Once again, that's part of our role as both regulator and manager of the national airspace. Next slide. So, what are cooperative operating practices? The industry defined FAA approved practices and how you will cooperatively manage the operations in the UAM airspace. Airspace management will be maintained by the FAA. We will structure the airspace to allow for these cooperative areas. But within the cooperative area, the strategic conflict management, the flow management, and the demand capacity balancing will be based on these cooperatively managed practices. And we will, so that if there's an excess of demand, the cooperative operating practices will specify how that demand is apportioned. In terms of flow, it'll help describe how the efficient flow is managed through the cooperative areas. And finally, like I said before, the cooperative strategic deconfliction, which is subject to some of the standards bodies right even today. Some of the COPs are focused on the aviation safety, and these fall directly within the FAA's regulatory mission. So the regulator is going to have to approve these COPs and the manner in which they're applied or supported by the PSUs. The other cooperative operating practices, such as avoiding unnecessary anti-competitive technical specifications for participation in the federated service network, that's a mouthful, basically says that the rules have to need to specify how equity will be maintained and what anti-competitive behavior would be from a participant. This is something that, we have had great practice with in our ground delay programs and airborne flow programs. We will do the same diligence to look at the cooperative practices, both in definition and in practice, to make sure that equity and fairness is maintained in the access to the airspace. And that's more of an ANSP role, because the airspace is managed by the air traffic organization. Next slide. So as Bob talked about, this really is dependent on what we call our updated architecture. You have the traditional NAS back there in the blue pillar, which is our industry data exchange protocols. This is where we get the information we need from you. You get information from us, like the status of the airspace, and other restrictions. And down below, from the service gateway out, is what would be developed by industry, where we have this network, which is managed by the PSUs. They share the information both with the UAM operators and with potentially the local public and the public safety organizations. The SDSPs would be people like command and control, communications providers, or weather, etc. And this new architecture where traditionally in ATC, you would have seen the green boxes, the green hexagons, hexagons, being the dividing line between ATC and the operational world. We've now moved that up all the way to the service gateway, where the actual operations are conducted through a federated network in cooperation with the PSUs and the operators. So that network lies at the center of this architecture. It's where we exchange the information. It's where every individual operator knows who's around them, where they're going, and what their intent is, so that we can maintain this in a safe and secure fashion. And one of the key new entrants would be, and we have UAM vertiport, but really the locations at which these vehicles will take off and land will have to be well managed in time, given the characteristics of these operations. Next slide. And with that, I am done. And I guess, Ann, it's back to you for questions.
Thank you. And you guys were so efficient. We're actually a little ahead of time, so we may get to more questions than we're usually able to.
I apologize.
No, don't. Not at all. So there's one rather long question, which I'm going to summarize, which asks how you are all taking into account human factors and human factors research in this environment. And I think that's really a question to all of you, so feel free to speak up.
Yeah, I mean, I can certainly start. I mean, it's sort of fundamental. We include our human factors researchers as a part of the development of the technology itself. So, there's a lot of issues with how you integrate humans and automation, and that's something that we're actively looking at. And certainly as you move towards autonomy and the role of the human and the autonomous system, again, really important issues that need to be understood and fully engineered in. So yeah, I think it's just part and parcel of all this, to make sure we understand the role of the human, how the human interacts with the systems, how the human and the automation partner to create the types of operations that are required.
So, and I'll piggyback on what Bob said, is we have two different roles. NASA really does focus on that more basic research of the aircraft research, where it's how is the operator going to operate the vehicle, how, and with these eVTOLs and the new methods, there's a lot there. Or as we go to autonomy, how are we going to maintain the remote operator in the loop? That's really a NASA role. That's not an FAA role. Our role is really what happens when you start to operate in the airspace. And so we're looking at the human factors of what's the interaction between operators in the airspace, what's the interaction between these operators when they deal with ATC, especially the autonomous vehicles, which may not fly in the cooperative areas. There'll be a real need for us to understand what's the relationship between a remote pilot and the air traffic system. And so this is an example where our research really is complementary and necessary because we have specific scope that we have to that we maintain. So we worry about you in the airspace. Bob does too, but he also worries about you in your aircraft.
Paul, anything you'd like to add to that?
No, I think they both covered it. I mean, it's obviously a consideration top to bottom. I know that the challenges that we'll have here in terms of moving to an autonomous environment and looking at what notions of one to many will be, I think is going to, present a lot of thought, a lot of education on both sides as to what that looks like. So I think, we get to really apply that sometimes in our operational demonstration activities and those kind of things where I think we really get to go from the conceptual to testing it and trying it. And that's where I think the human factors aspects really kick in at that point. So yeah, it's a consideration right from the get-go.
Thank you all. So another participant would like to hear about the legal framework being worked to ensure protection of airspace rights of residents and development on the ground. Airspace corridors not operating below a defined minimum air elevation beyond certain takeoff and landings, excuse me, overpopulated development areas. Has thought been given to alignment of air corridors over already defined on the ground transportation corridors?
So I guess I can start the conversation here on that. I mean, obviously, I think what you're going to see here coming up in the 2024 timeframe is when we really get out of the certification phase for many of the applicants and these vehicles starting to show up on the scene. And we really start to talk about what the integration issues will be in terms of the deployment of them. And as we start to move along, I mean, there's a lot of parties that have to be part of that conversation, right? So not only the, it's certainly when you look at how we structure our activities with noise around airports today, there's really a community engagement process that we go through that supports that. So I expect as routes and everything get defined, I think that's still a future activity to come. We'll go through similar processes that I think have been tried and true for us and working, right? But it is a overall, it's not just an FAA responsibility. It's really a community responsibility, as well as the manufacturers and the applicants that are trying to put these things into service. So I think working together, we can all work to make sure that we come up with something that balances the needs of everyone, right? In terms of the operational requirements to support it, but the community interest as well.
I think that's right. I think one of the things we've seen in surface transportation is a significant fragmentation of how those applications are applied. I think one advantage that we have in the aviation space is the FAA is there overseeing the airspace. So I commend you. Commend your leadership.
And to just add too, I mean, I'd be remiss in not saying, right, that the most interesting aspect of all of these, right, is that this will, as electric vehicles, this is not at the same kind of noise profiles that we've experienced in the past. So I think that's where a tremendous amount of relearning, right, and trying to figure out exactly what these are. I think there's going to have to be a public acceptance and warming up to this new form of transportation that'll be at a lower noise profile than we've seen with more traditional aircraft. So I think, like I said, that's part of what everyone's going to have to see, touch, and feel and experience to understand what that's going to look like as it appears to the community.
I also like to, the FAA doesn't build vertiports or landing pads. Where those are located is local communities and zoning. And for one thing, the next thing is, what is its purpose? I mean, if its a purpose as a transit point, then it really becomes a ground surface transportation issue. Where can you locate it? What are the roads feeding it? What's the power? So there's so much more than just the airspace involved in this industry as it evolves. And most of those are not questions for the FAA. Some of them are questions for UAM at Volpe as a larger transportation. And then, you know, we do not decide all this by ourselves, thank God. I think was what Paul really wanted to say when he started this question.
Bob, anything you'd like to add to that? Except that you're glad you're not in the.
Yeah, exactly. Yeah. We're certainly at least once removed from that. I guess the only thing I would add is that we certainly, you know, as we work with entities in developing research results and so forth, you know, to the greatest extent possible, you know, that we get the right inputs from our partners as to what the problems are. Our research results can inform the results and the policies and so forth. And so we try to be sensitive to that while we don't have a direct role.
No, I'm probably overstating it, but I think the government as large understands this. That's why our Congress does. That's why we have the interagency working group, because there are many aspects to it besides just flying in the airspace.
Thank you for mentioning the interagency working group. I'm just trying to figure out how to fit that into the conversation. I think that is an important space, and people need to pay attention.
And NASA participates in the interagency working group.
And we do. We participate.
So he's not really once removed. He's in the midst.
Yeah. So, Bob, on a completely different topic, one participant mentions that, or picked up on the fact that you said, unfortunately, the X-57 plane wasn't taken to flight. How did you rationalize that no-fly decision?
Yeah. So, to get into
not too sensitive.
No, it's not. I mean, just to get into a bit more detail. So, it's a really interesting project. When we started it, we wanted to make sure that we were supporting the development of U.S. industry, and so we chose U.S. technologies at the time, and this is quite a few years ago now, and many of the technologies were at lower TRL than we had anticipated. One of those being the drive engines, the cruise engines, or cruise motors rather, and so along the way we had to go back to the drawing board and do a lot of component redesign and redevelopment. A lot of that work we did in-house between the Armstrong Flight Research Center and the Glenn Research Center. And we basically solved problems along the way, and we published all of that so that industry was aware of the kinds of challenges you can run into and how to solve them. But in the final analysis, we were getting close, and we ran into a bearing problem on the cruise motors that would have taken a substantial redesign to ensure that those motors would be safe for flight. And that's when we had to make a decision. It was probably going to extend the time to first flight by almost a year. And of course, schedule is money, and so we had to make a trade-off with other things that other parts of the AAM portfolio, and we decided that in the big picture, what we had learned versus what more we had to learn by going to flight, it was the better decision was to end the program at the end of FY23. So, which is what we did. We have a little extension into this year to wrap things up and write additional papers and capture lessons learned and capture technology learnings and so forth. So we have a little bit left to do, but that was the unfortunate part. If we hadn't run into that last problem on the bearing, we would have gone ahead and flown.
Thank you. So, question probably mostly for Stephen and Paul. Will FAA regulate the operations of eVTOLs, for example, using the UAM corridors? Will there be a minimum or maximum speed limit? Or is it too soon to tell?
I think it's too soon to tell. I think that if the performance characteristics are so different between the eVTOLs, then we probably have a problem with the concept, because they've either we have a problem with the concept, or the time-based management becomes really, really important, so that when they enter the corridor, they're not going to chase over the aircraft ahead of it. And we'll see how that goes. I mean, I think one of the principles in the back of our mind is that they may all operate in a range, which would make this easy, but it could be that it's hard, and we'll find that out. That's one of the things we have to learn about this. Or, do I have to have a fast lane and a slow lane in the corridor? These are all things to be examined. But it's certainly a consideration, something we worry about, not worry about, think about. We don't worry about anything. We just think a lot. But it's one of those considerations that we keep thinking about. Paul, you're getting excited.
I would say, and once again, I think that's one of those discussions really that's important to have amongst the industry members themselves as well, right? I mean, we're trying here to conceptualize what that looks like. And like Steve said, it's probably, excuse me, a little too early. But those are kind of the operational considerations, right? Once we, see the performance envelope of these vehicles, and how will that practically work? And industry will play a key role, right, in helping determine that amongst themselves as well.
And we're, speaking of corridors, so we've certainly run corridor simulations, and it's in some ways it's a good research question as well. We can we can look at variations of performance with respect to the to those corridors and the performance of the corridor itself and so forth, and the kinds of things you would need to do to both make sure you've got safe operations, efficient operations, and adequate separation and so forth. So, but so far at least the simulations we've done really do show there's a lot of promise to the corridor concept.
So another, excuse me, operational question that maybe you're not worrying, thinking about. Would vertiports be responsible for their own landing takeoff clearances, and how would that integrate with the common operating areas?
I would I'd start from a research perspective, and then Steve can kind of say what the the better answer is. But I think that's a functional allocation issue that we've been looking at. What is how do you divide those decisions and functions up amongst the the vertiport itself, the airspace, and then the vehicle, to try to get both the efficiency, performance, and safety that you need. So I think it's an important question that we need to work through from a research perspective.
I think it's fairly clear that these are time sensitive type of operations. So there will be a schedule for both when you depart and when you land, and how that's allocated. That's, like Bob said, that's probably, subject for research. I think most of us would guess it's probably the operator, but who knows? Because you have to. It's almost like you have to have a gate when you get there, in how you fill the gate. But it's really time sensitive operations, and so whatever there is, there's going to be a schedule. There's not a lot of time to wait.
Yeah, there's just a tremendous amount of considerations there, right? In terms of cycle times, turn times for loading and unloading, charging needs, and those kind of things. And so I think that's one, as we gain more practical experience, right? That's going to continue to evolve in terms of what that looks like. Can those functions be automated? How do you schedule those things? As Steve is saying, schedule is going to become absolutely imperative there, in terms of managing the time aspects of those pads.
So, I mean, it also depends on where is it located. Is it at a public airport? Is it a public facility, or is it a private facility too? Same considerations we have with regular aircraft. We'll have to go through all those.
So has, maybe it's the last question, maybe have time for one more. Has there been any coordination and or interoperability of communication protocols with between the UAM space and the surface transportation space? Do you see opportunities for optimization across the overall transportation system, particularly if you see the vertical takeoff ports as intermodal hubs?
I personally think that's up to the transportation companies. You know, are they taking you to the vertiport are they part, is it part of an end-to-end transit scheme, or is it, you know, more like you and I did today where we drive to the airport? I don't think we have, I think they have to be integrated to some extent, especially if it's in an urban area. I don't think you have a lot of places to park. And I know some people say we can put them on parking garages, but in my experience, parking garages are always off a back alley behind a building, and I can't see that as a major transport hub. So, you know, I think there's a lot of these considerations that we really have to work our way through in the next couple of years. But rather quickly, and it does require us to work together, both surface and air.
Bob or Paul, anything you'd like to add to that?
No, I mean, I think if you look at just transportation today, you know, your airline reservation linked to your car reservations and everything has just become a capability that, you know, that the companies count on today. And it's all about the data, right? And making the data available to support the multiple pieces that hang off of that, right? So since that's already a trend that's going, I think that becomes a more automated function more and more, as long as that data is made available to others, right? So I do think it becomes a little more seamless as we move forward. And certainly I think the various companies pursuing this want to make this as seamless an operation, you know, to an expeditious an operation, right? To make sure that the paying customers get the service that they're anticipating.
Yeah, I think that's right. You know, if you think about this, the timeline, the scalability and so forth, we're probably a decade out to when this is a really scaled transportation system at the earliest. And so you think about what things should, you know, how this should all work at that point. And yeah, these should be very seamless. And I think one interesting question is, you know, is it the provider that's doing an end-to-end service and trying to control all of that data and the operation, or is it the customer who, like in real time, can shift his plans across modes, across providers, and so forth? So who's going to win that fight in terms of that race competition, in terms of who's making the decisions on your end-to-end trip?
Edge computation.
So we're almost up against the hour. Thank you all for really interesting, not only presentations, but discussion. There are a lot of really good questions that I wasn't able to get to, and I'm sorry. But one of my takeaways from this session, and honestly, I hadn't expected it, is beyond the technology and the engineering are the complexity of the institutional and intergovernmental to industry questions that need to be resolved as we move forward. So thank you for your leadership. Thank you for a great discussion and sharing your perspectives. We continue to have great engagement in this series across the transportation enterprise. And I'd like to thank everyone for linking in at such a busy time of year. We're going to take a break with the holiday season and reconvene the series about a month from now on Wednesday, January 17th at 1 o'clock. That will be in 2024. At that time, we will discuss environmentally responsible integration of AAM. Opening remarks will be delivered by Julie Marks, the Acting Executive Director of the Office of Environment and Energy at the FAA, and we'll have two featured presentations, one from Dr. Stephen Rizzi, Senior Researcher for Aeroacoustics at the NASA Langley Research Center, and Christopher Roof, Chief of Environmental Measurement and Modeling here at the Volpe Center. So have a great holiday season, everyone, and we look forward to seeing you in the new year. Thanks again for your time.
Thank you, Ann. Thanks, everybody.
Thank you.
Thank you.